Hi everyone, welcome to the video lesson for Monday, February 8th and Tuesday, February 9th. In this lesson, we learned about balancing reactions. Before we got to those notes, we had the following warm-up. I gave you these three chemical equations and I asked you to categorize them using the 5 types of reactions we learned about last week. We learned about synthesis, decomposition, combustion, single replacement, and double replacement. So my first one here, I have Si plus Cl2 yields SiCl4. So I have 2 reactants forming one product. This is a synthesis reaction. Remember, my synthesis reactions will always have multiple reactants, but only one product. My next equation is Cl2 plus KBr produces KCl and Br2. This is a single replacement reaction. I have a lone element, my Cl, with an ionic compound, KBr, and my final products are a single element and an ionic compound. Single replacement reactions always have a single element and an ionic compound as their reactants and their products. And finally, I have C3H6 plus O2 yields CO2 and H2O. That's a combustion reaction. Our combustion reactions always involve a hydrocarbon, so a compound made of only carbon and hydrogen, although sometimes we can throw an oxygen in there, reacting with O2, oxygen gas, to form carbon dioxide and H2O. We always get those same products from a combustion reaction. The only thing that's going to change in my combustion reactions are the subscripts on my carbon and hydrogen in the hydrocarbon and the coefficients. Your homework tonight, before I see you for the second class of the week, is to finish up that balancing and type homework. So by now you should have finished over the weekend. You should have finished classifying all of those reaction types. After today's notes, you'll know how to balance reactions. So you're going to need to go back into that Google Slides and balance them before you hand in that homework. After we finish going over our warm-up, I asked you to go into our module. Underneath first class of the week was a link to get your newest copy of our newest Google Slide notes all about balancing. It looks like this. Remember, once this loads, please sort this into a chemistry folder into your My Drive. That way you can easily find your notes whenever you're taking a checkpoint or working on a homework. Now, you might notice that there's not a table of contents in this Google Slides document. There's only 2 pages of notes, 3 pages of examples, and then I embedded 3 YouTube videos. So I did not feel that there were enough sections to warrant a table of contents. So we start right with the notes onto slide 2. The conservation of matter. Now, this is an overall law of the universe. Matter is conserved. Matter is conserved during chemical reactions. Matter is not created or destroyed. So whatever atoms I start a chemical reaction with are the same atoms that need to be there when a chemical reaction has finished. In a chemical reaction, we are not creating or destroying atoms, we are simply rearranging them. We're breaking and creating chemical bonds to make new molecules from the old same atoms. Therefore, in order for a chemical reaction to be balanced, we need to have the same number of atoms of each type of element on either side of the arrow in a reaction. We can make sure that the numbers of each type of atom are equal by adding more molecules to either side of the equation. By adding more molecules, we increase the number until we have equal amounts on either side. Once we know that we have enough, we show this in the equation by updating the number, or the coefficient, that comes before each molecule in a reaction. So In order to balance reactions, I have 3 different rules to follow that have 3 sub-rules attached. The first rule is that you need to count up the atoms on each side of the equation. Find out how many of each type of atom, each type of element you have to begin with and to end with. Now, my sub-rule here is that you should not break up polyatomic ions unless you have to. On your homework and on your checkpoint, I've already started to help you out with this. Rather than just giving you the chemical formula, I've been making you little images to go along with chemical formulas. So if there's an NO3 on either side of the equation, little figure of an NO3, that means you should count it as NO3, as a nitrate, instead of counting it as a nitrogen and 3 oxygens. In the chemical equations where you do need to break up the polyatomic ions, I've already done that for you. For example, in one of your homework problems in the Google Slides, there's carbonate, CO3, but since it gets broken up within that equation, I actually wrote it for you as carbon and 3 oxygens. So this year I'll be helping you out, but for quite a few of our practice problems, it might not tell you that it's a polyatomic ion. You'll have to identify that yourself. Once you've added up the total number of each type of atom, figure out what you need more of. Add more of that molecule, which is the same thing as changing its coefficient, until you have equal amounts. And I will say that sometimes just adding more isn't enough to get to an equal amount. Sometimes it's a little bit like those ionic compounds that we had to balance. You always add more of what you need more of, but sometimes that unbalances it again, and you have to go back and forth. Now, my sub-rule here is if you get the option, you should always start by balancing carbon. Now, carbon is not in every chemical reaction. So you often don't need this rule. But whenever it comes to a combustion reaction, this is a very helpful tool to help you balance your reactions. And our final rule is just to repeat steps 1 and 2 until there are equal amounts of each type of atom on either sides of the chemical equation. As soon as you start adding more of one type of molecule, you need to go back and recount all of the atoms on that side of the equation. Changing one molecule usually changes more than just one type of atom. And my sub-rule is that you should always wait to balance your oxygen last. You will sometimes need to go back and fix other compounds and elements before you're able to really finish up your oxygen and have it balanced. So I always save oxygen to last. And just to remind you, sub-rules are not hard and fast. These are rules that are sometimes followed, but are just as often not followed. These are just little guidelines that help make some really difficult questions just a little bit easier. So here's our first example. H2 plus O2 yields H2O. So in your Google Slides, you do need a Control-C, Control-V to copy and paste your molecules. Here I've got drag a copy. But the first thing I want to do is find out how many total I start with. So here's one molecule of H2, one molecule of O2, and one molecule of H2O. So I'm going to start things off by counting up my totals. So on my reactant side, I start with 2 hydrogens and 2 oxygens. And then on my product side, I'm going to start off with 2 hydrogens and 1 oxygen. So in our notes, we count our totals. We find out what do we need more of. I can see that I need more of oxygen. I only have 1 oxygen on my product side, but 2 on my reactant side. Now, I know the rule said balance oxygen last, but my hydrogen is balanced. So I don't need to balance anyone other than my oxygen, so it's okay to start with oxygen. So over here on my product side, I only get oxygen from water. So I need another water molecule, H2O. So now I have new amounts. So I'm going to update my count. I now have 2 oxygens over here on my product side. I'm going to cross out my 1 and I'm going to write 2. But changing the number of water molecules also changed my number of hydrogens. I had 2 hydrogens, but now I have 1, 2, 3, 4. Now, something that we are getting a huge benefit from in virtual school this year is when I do this with students in person, they tend to just want to add more oxygens by themselves to the reaction. We can't do that. You have to add the entire molecule. You can't change the reaction. So now I'm giving you these images of the molecule, so you have no choice. You can't break it up. You have to use the entire molecule another time. So now I want more hydrogens. Now it's nice and easy because hydrogen only is by itself on the reactant side. So if I add one more H2 molecule, now I have 1, 2, 3, and 4. So I'm going to update my count of hydrogens. There are no oxygens here, and I didn't change my oxygen, so I don't need to update my oxygens. And now I'm balanced. I have 4 hydrogens to begin and end with, and I have 2 oxygens to begin and to end with. So now the last thing I need to do is to write my coefficients. So in order to make this a balanced equation, I used 2 molecules of hydrogen. So this coefficient is a 2. I only used 1 molecule of O2. So this coefficient is a 1. And then I used 2 molecules of water. So this coefficient is a 2. Now, I like my students to start with balancing equations by using these images, but there's also a mathematical way to get here as well. Notice, my coefficient of 2 times my subscript of 2 gives me 4 hydrogen atoms. 1 times the subscript of 2 gives me a total of 2 oxygen atoms. 2 times the subscript of 2 gives me 2 hydrogen atoms, gives me 4 hydrogen atoms, and 2 times the subscript of 1 gives me 2 oxygen atoms. Here is our second example of a problem to balance. So I'm going to start by seeing how many of each type of atom I have to begin with. So I'm moving these up. So on my reactant side, I'm going to start with 1 aluminum and 2 oxygens. And on my product side, I'm starting with 3 oxygens and 2 aluminums. So according to my rules, I should always start with carbon first, and there are no carbons here. And oxygens last, and I do have oxygens. So I'm going to focus on my aluminum to begin with. I have 2 aluminums and 1 aluminum. So I'm going to add more aluminum atoms. Now notice I can add exactly how many I want here because aluminum is an atom by itself. So I had 1 aluminum. Now I have 2. So my aluminum is nice and balanced. So now it's time to balance my oxygens. I have 3 oxygens on my product side and 2 on my reactant. So I need more on my reactant side. So let me add another molecule of oxygen to my reactant side. Let's update the count. And so I had 2 and 3. Now I have 4 and 3, and oh no, I'm just as far away as I was when I started balancing that. Notice it doesn't matter how much I add to my reactant side, they're never going to be equal. As long as on my product side, I have an odd number of oxygens. So we can also see this as now I have too much oxygen on my reactant side, so now I need to add to my product side. Remember, you can always add more molecules. You really shouldn't be taking them away, and you can't break them apart either. So let's add another product. So now I've changed my number of oxygens. I had 3. Now I have 6. But by adding another Al2O3, I now have more aluminums. So it's no longer 2. I now have 4. Now, in trying to balance my oxygens, I have now unbalanced my aluminum. I always like to go and fix the thing that we screwed up before I continue on. So I'm going to go and fix my aluminum. So my aluminum was fine until I doubled it over here. What I'm going to do over here is double it. I'm going to get a total of 4 aluminums. This is all about ratios. So since I doubled this one here, I can just change this to 4 here. That is true. But I can also think of it as doubling my amount. When I double my amount, then I've also fixed it another way. I've done the same thing, but it's just another way to think of it. So I no longer have 2 aluminum on my reactant side. I now have 4. Now I can go and fix my oxygens. I have 4 oxygens on my reactant side, 6 on my product side. So I'm going to add 1 more oxygen here. And let me recount. 1, 2, 3, 4, 5, 6. So 4 is no longer my amount. I now have 6. So I have 4 and 4 aluminums, 6 and 6 oxygens. My reaction is balanced. So I'm going to update my coefficients. I have aluminum 1, 2, 3, 4. I have my oxygen 1, 2, 3 times. And I have my aluminum oxide 1, 2 times. So however many times I have that molecule is my coefficient. Remember, don't be looking at the ones at the bottom. This is just where I've been pulling my molecules from. And our last example in our Google Slide notes is this combustion reaction. Now, there are 2 types of combustion reaction problems. They're the ones that are very easy to balance and the ones that are much more difficult. This is one of the more difficult ones. I chose this one so you could see how to solve one of the more difficult combustion reactions. And there is at least one of these in your homework as well. This balancing problem starts the same way all of our others have started. I want to have one of each type of molecule and count up the totals. On my reactant side, I'm starting with 2 carbons, 6 hydrogens, and 2 oxygens. On my product side, I have 1 carbon, 2 hydrogens, and 3 oxygens. Something I think is kind of neat. Every single combustion reaction always ends with 1, 2, and 3 for my carbon, hydrogen, oxygen. Neat little pattern. So I need to see who do I need more of, who is unbalanced, and well, all of my elements are unbalanced. My rules say to start with carbon if I can, and I need to balance my carbon. And it also mentions that I should do oxygen last, so I'm going to take care of my carbon and then my hydrogen, and then I'm going to start looking at what I need to do to fix my oxygen. And this is true for the hard and for the easy types of combustion reactions. So I have 2 carbons here on my reactant side, only 1 over here on my product side. So I'm going to take and add 1 more molecule of carbon dioxide. So now my carbons have changed. I had 1 carbon. Now I have 2. I had 3 oxygens, but now I've changed my total number of oxygens. I now have 1, 2, 3, 4, 5 oxygens. So my 3 oxygens is now a 5 oxygen. Okay, now my oxygens are pretty unbalanced, but I want to wait until the end for oxygen. So I'm going to take care of my hydrogens next. I have 6 hydrogens here and only 2 hydrogens. So if I add one more water molecule, I now have 4 hydrogens. So I'm going to add another water molecule. Now I have 2, 4, 6. So now my hydrogens are equal. So let me update my chart. 2 is now 6. But adding all those waters has now changed my oxygen as well. So now I have 2, 4, 5, 6, 7 oxygens. And here's where a combustion problem becomes a hard to balance combustion problem. If you have an easy to balance combustion problem, you will have an even number of oxygens on your product side. What makes this a challenging combustion problem is I now have an odd number of oxygens. This is what makes it so difficult to solve, because I can only ever have even numbers of oxygens on my reactant side. So I need to fix my odd number of oxygens. Now, I'm getting an even number of oxygens from here in my carbon dioxide, and my odd number is coming from here, my water, because I only get 1 oxygen per molecule, and I currently have an odd number of molecules. Now remember, balancing equations is all about ratios. I can't really take away any of these molecules, but I can add more. And it's not so much adding as multiplying. So the easiest way to turn an odd number into an even number is to double it, to multiply it by 2. So I had 3 waters here. I'm going to double that amount and have 6 water molecules instead. Now I have an even number of oxygens plus an even number of oxygens. I can work with this. But making that change unbalances my hydrogens. So I need to go and fix that. So let me take my new tally. I did have 6 hydrogens, but I doubled it. So 6 plus another 6 means I now have 12 hydrogens. I did have 7 oxygens, but now I have more. So let me recount. I have 2, 4, 6, 8, 10 oxygens. That was 7. It is now 10. Now I'm not going to go and fix my oxygens because I just messed up my hydrogens. So now I'm going to come back to my reactants and fix my hydrogens. So I have 6 hydrogens. I need 12. So what I need is to double this. So by adding another molecule, I've doubled my amount of hydrogens. So what was 6 hydrogens is now 12. But changing my hydrogens also changed my carbons. I had 2, but now it's been doubled to 4. So now my hydrogens are balanced, but balancing my hydrogens has unbalanced my carbon. So now I need more carbons on my product side. I had 2, but then I doubled my amount, so I need to double my amount here. So 2 becomes 4 molecules. So if I'm going to retally up my atoms, I now have 1, 2, 3, 4 carbons. And my total number of oxygens is 2, 4, 6, 8, 10, 12, 14. So I had to double my water molecules, which meant I then had to double my hydrocarbon, and then I had to double my carbon dioxide. But now I have an even number of oxygens on my product side. I satisfied everyone else. I now have an even number of oxygens, so I can divide 14 by 2 to balance this. So I have 1 molecule. 2 molecules gives me 4. 3 gives me 6. 4 gives me 8. 5 gives me 10. 6 gives me 12. And 7 molecules of O2 gives me 14 atoms. And since oxygen is by itself, adding more here doesn't affect my carbons or my hydrogens. I have equal amounts to begin and end each of my types of atoms. So now all I need to do is update my coefficients. I use this molecule 2 times. I have 7 of this molecule. I have 1, 2, 3, 4 carbon dioxides. And I have 6 water molecules. For all of your checkpoint questions, you always need to write in your number of molecules. Never leave it blank for 1. If the answer is 1, you need to write in a 1. That's all we had time for during class today. Don't forget there are more resources in your class module. I have a page full of websites with more practice tools and practice games. And there's the Gizmo. The Gizmo is intended as self-guided notes. It is not a homework assignment. It does say classwork, but there are no points. The Gizmo is another way to visualize balancing your chemical reactions. In the work that I've given you images of the molecules so you can see the individual atoms. In the Gizmo, it shows you the individual atoms, but not necessarily in a molecule. It's another way of looking at equations, and it's a very powerful, very helpful tool. I highly recommend looking into it and trying it if you haven't already. Remember, you can use these notes on your checkpoint, which is going to be starting later this week. Until I see you guys again, stay safe and make good choices, everyone.